And now we can plug into E equals mc squared. What should we plug in for m?
Well, I multiplied it out.
Oh, you already did the calculation? Okay.
28.295,244.
And what are the units on that mass?
Mega electron volts over c squared.
Good. And what are we multiplying that by?
Speed of light, so 3 times 10.
Now, instead of doing that, let's just say we're multiplying by c squared. Because what's going to happen now? That's right. The nice thing, the reason that these units are convenient, even when they seem difficult at first, is that it allows the c squares to cancel here. So we never actually have to plug in the 3 times 10 to the 8th over here. Oh, yeah. Boards right to each other. But anyway, we can just do this. So what do we end up with as our answer?
28.295244.
And the units are?
Mega electron volts.
And are those units for energy?
Yes.
Yes, so all the units did work out eventually at the end. So as is often the case in physics, one of the trickiest parts is the units. One of the hardest things about working with the mass defect and binding energy is working with these weird units. .3? Yeah, that's what we got. Good. Let's review the steps. The question was asking us for the binding energy. But in order to find the binding energy, first we have to find the mass defect. We have to figure out what the total mass of the protons and neutrons would be if they were separate and subtract what their mass is in the nucleus. And all of these are numbers we have to be given. We can't just use our standard numbers of 4 and 1 and 1, because those are only approximations. So we looked up in the table what the exact mass of the protons and the neutrons was. Of course, you have to take into account how many protons and neutrons there are. These numbers wouldn't always be 2. They were only 2 because it was a helium nucleus. And then we also have to be given what the actual mass of the helium nucleus was, and we subtracted to find the mass defect. Notice again that even though the table had 3 columns, we're probably best off using the column for atomic mass unit, at least for your course. That seems to be the column that your instructor prefers. So we use the atomic mass unit, not the kilograms of the third one. Then before we plug into E equals mc squared, we need to get out of U's and into these units. These units turn out to work much better in the E equals mc squared equation. So we had to make this conversion. That was a very easy conversion because we just took this number and multiplied by 931.5. And the nice thing about these new units, mega electron volts per c squared, is that when you plug it into the E equals mc squared, the c squareds cancel. And you never even have to bother plugging in 3 times 10 to the 8th. And you're left with just the mega electron volts. So definitely, I think really the trickiest part here is the units. That's the part you really have to practice and highlight clearly in your notes. Try problem 4 here.
So for this one, we're just dealing with this on its own, correct?
That's right.
Okay.
As
Not really taking into account like the rest of the question, that problem.
Well, let's see. Let's take our time and we'll see.
Okay. No, we have to find the mass defect first to find the binding energies, mass of the protons. Oh, I guess we can. So that means that there's 2 neutrons and 1 proton. So, okay.
Yeah, actually we should take into account the type of decay they're talking about here. So in this case, we're not really envisioning splitting this up, strictly speaking, into protons and neutrons. Instead, they said instead of a proton, it's going to generate a hydrogen. And I guess they're thinking of a hydrogen atom here. So we're going to try to figure out what the binding energy is in this equation, where we go from this nucleus into these decay products over here. How many neutrons are we getting?
2.
Okay, well, just as before, in this type of decay, again, this mass will be bigger than this mass because we have to add energy in order for this process to happen.
Do you know the mass of the nucleus? Or I guess is that considered the mass of the nucleus?
That's right. That's what they say, right? The tritium has a mass of.
Okay. And then you multiply that by 1.5.
Good, because what are the units on this number?
U.
Good, and what concept does this represent?
Mass.
The mass defect, right, that's the mass defect, but we know that mass would be more conveniently expressed in these units. Good. And you got the right units, mega electron volts per c squared. Great. What's the answer to part A then?
8.482239 electron volts.
Mega electron volts, right? Now this problem was a little different than before because we're looking at a slightly different type of mass defect and binding energy. Instead of strictly speaking breaking the nucleus all the way into neutrons and protons, we had different decay products. We broke it into a hydrogen atom and neutrons, but we can still have analogous concepts. The binding energy is how much energy it takes to break up that nucleus. And then the mass defect, we would still expect that these separate components have a greater mass than when they're all in the nucleus together. So that still gives us the mass defect here. Obviously, we have to work with the concepts they're telling us about because that's what they gave us the numbers for. So this was the mass for the hydrogen. That's right, this was the mass for the hydrogen, and they gave us the mass of the 2 neutrons, and they gave us the mass of the tritium nucleus. One thing that you have to remember in the future is it would be very tempting maybe at this point to divide by 3 times 10 to the 8th, but we just want to leave this as a c squared because we know in the back of our mind that's going to cancel at this step. So in fact, there isn't really any new calculations we have to do here. Once we do the unit conversion, we've almost got the answer in our lap numerically.